So today in this lecture we will see that what is present inside the galvanometer. So inside the galvanometer we have these parts. So inside the galvanometer we have this magnet. So this is actually a magnet, okay, and along with that we have this coil. Okay, we have this is the coil is. So this coil is made up of large number of the conductor which is wrapped around a insulator, and inside this coil we have a drum like shape. This drum is actually a ferromagnetic material and which is used to enhance the magnetic field of this coil. If we provide the current to this coil, okay, when the current is flowing in the conductor, it will produce the magnetic field, okay. Then this coil will behave as a solenoid and it will produce the magnetic field inside it, okay. And that a magnetic field produced by this coil, okay, produced by this coil will enhance by this ferromagnetic material which is present inside it. The one side of this coil will be the north and the other side will be the south. And if we put this coil, okay, inside this magnet, if we provide the current to that coil, the current will flow in that coil will produce the magnetic field around itself, and that internal magnetic field due to coil will interact with this external magnetic field, okay, that will interact with this external magnetic field, and due to which, okay, the force will exert on that coil, and due to which that coil will rotate inside this external magnetic field, okay. So here if we see that inside so this magnet is actually, we have the concave like shape, okay. This concave shape is because the magnetic field line will always at any angle of the coil will perpendicular to the area of the coil. This is actually the area of the coil. This side is actually the area of the coil. The external magnetic field due to this magnet will always perpendicular to this area, okay. That's why we choose this concave like magnet, okay. So here if we see carefully, in the upper part of this coil we have a spring like shape. We have this spring, okay. This is actually a spring, and similarly at the lower part of the coil we have this spring. This is the spring, okay. So what is the function of these springs which is attached on both side of this coil, okay. So because if we provide the current to this coil in the external, and this coil is present in this magnet, okay, in this magnet, then the magnetic field will produce around this coil due to the current that will interact with this magnetic field of this permanent magnet, due to which the force will exert on this coil, okay. The force will exert on this coil and this will show the deflection, okay. Now on either side of this coil we have springs. So if it move, okay, if it rotate, then at that time this coil will be twisted. When we rotate this, that coil will twist, okay. And if we remove the current external, okay, then it will move again its to its original position. So these springs are used to bring the coil again to its original position, okay, to bring the coil again to its original position. So in the galvanometer we have the pointer like shape which indicate us that is the current, how many current you provide to galvanometer. So that indicator is actually this is that indicator, okay. This is directly connected with this coil. This indicator is directly connected with this coil, and if this coil is moved, then this indicator will be moved, and then it will show us the uh, a specific calibration, okay. So now here in this apparatus we have two types of the torques. One torque is produced due to when we provide the current to this coil, okay, then this coil will move. So this coil will be rotate. So the first torque is that, okay, and which is given by torque is equal to, okay, due to current is equal to, which is given by N, okay, I A and B sine theta, which is given by this N I A B sine theta. So here this N, this torque is actually the torque on this coil, and this N is actually the number of the turns in this coil. This coil is actually made by the large number of conductors. So here this like conductors, so the number of the turns we will put that here. This torque is depend upon the number of the turns and also the provided current. If we provide more current, okay, then this torque will be more, okay. This is that current. A is the area of this coil, this area, okay, this area of the coil. B is the external magnetic field. As we discussed that if this move, okay, if this if the torque is produced in this coil, it will twist the spring along itself. So here these springs on either side of the coil will be twisted along uh, the turning of this coil, okay. So the second torque is produced in these springs, so which is given by, so that is actually a restoring torque. Restoring torque. That is actually a restoring torque, which is directly proportional to the theta. The restoring torque is directly proportional to the theta, and this theta are the phi, okay. Let's say this is phi, so this phi or theta is actually the angle made by this uh, angle made by this pointer, which is directly connected to the coil, okay. So at this position, okay, so here this phi is 0. If we provide the current to the coil, it will move. So here this is 0, okay, then it will be move, okay, then it will be move, okay. So here it will make the angle, it will make the angle. So that angle is given by phi. So this so it, if it move if it rotate more, okay, then that phi will be more. So here this restoring torque is directly proportional to phi, okay. And if we instead of this proportionality sign, we will put is equal to n constant. So here this tau restoring, and instead of this we will put is equal to a constant. Okay, and we have that same phi, and instead of this constant we will put c. So tau restoring is equal to c and phi. So now we have two talks. One is this and the other one is this. So we have these two talks. Okay. So if these two talks become equal, it means that if this torque, the torque due to this coil is equal to the torque and in these springs, okay, this spring which is present on both side of this that spring, okay, which is present on both side of this coil. Okay, we have one this spring and the other one is this spring. Okay, so this torque is due to that spring. So if these both become equal, okay, this will be zero. Then this the coil and the torque due to coil and minus the torque due to restoring torque, the torque due to springs will be equal to 0. So here if I bring this to the other side, so tau beta is equal to tau uh, restoring. Okay, so here I will put these values. Okay, the tau b is given by NIAB sine theta n. So this is given by NIAB sine theta, which is equal to tau restoring is given by C, and we have 5. In this case, this sine theta, this theta will be 90 because here this magnet have concave like shape, and at every position, at every angle of this coil, it will be perpendicular to the external magnetic field. Therefore the sine 90 is equal to 1, and we will put 1 instead of this sine theta. Okay, so NIAB is equal to C phi, okay, this is the C phi, and in this case this C is actually a constant. Okay, so here in this case I is equal to C divided by NAB into phi. Okay, so here this C is actually a constant. We have constant. This C is the constant proportionality for the restoring force. Similarly, this N is the constant. This N is the number of the turns on this coil which is constant, and this A, okay, we have this A is the area of this coil which is also constant, and B is the external magnetic field which is constant for this device. So these all are constant. Okay, so if we have constant and equality sign, then we can put the proportionality sign for these two, for the constant and equality. So then it will become I is directly proportional to the angle. Okay, it means that if we increase the current to the galvanometer, okay, if we increase the current to the galvanometer, then more deflection, this phi, more deflection will be occur. Okay, so this I is directly proportional to phi.